In the second part of this exercise, you'll take the 10 kilo ohm resistor that you've used previously and measure its resistance directly by measuring the voltage across it when a current is forced through it. We're going to use a digital multimeter to measure voltage and another digital multimeter to measure current. So we'll get some reasonably good measurements of voltage and current and then calculate the resistance with its uncertainty. The resistance R is simply voltage divided by current. R is V over I. So our first task is going to be wiring up this circuit diagram, and in this diagram the battery symbol, we will use that to represent a power supply. There's the symbol for a resistor, symbol for a digital multimeter used as a voltmeter, symbol for a digital multimeter used as an ammeter. And basically the lines joining those symbols represent wires joining the various components. So our first task is to turn that circuit diagram into an actual circuit. The simplest way to convert a simple circuit diagram into an actual circuit is to basically lay things out approximately as they were in the circuit diagram. Now, our first task, let's just connect up the power supply to the resistor through the current meter and back to the power supply to provide the basic circuit. So we'll simply plug one wire from the power supply to the resistor. We then need to connect from the resistor to the current meter, and since I'm going from the positive side of the power supply through the resistor, I'm going to go to the positive side of the meter because I'm coming down from positive towards negative, and then finally I'll connect back from that meter through the common input back to the power supply. And that basic circuit provides the current that flows through the resistor, through the meter and back to the power supply. Now the next thing we have to do is to measure the voltage across the resistor. And to do that we need to connect the digital multimeter we'll use as a voltmeter, again positive side of the voltmeter to the positive side of the resistor, and the negative side of the voltmeter or multimeter from the common input to the negative side of the resistor. So now we're measuring voltage across that. We'll simply turn these around now to make them a little bit easier to read. Try and get the wires a bit out of the way. Turn on the power supply and we'll turn that on to read voltage and this one on to read current. I'm turning it all the way around to the milliamp setting. And I've got that now on the DC voltage setting. For a moment there I had it on AC voltage so I wasn't seeing anything. But DC voltage, I'm seeing 3.86 volts and about 70.7 milliamps. So we're reading again 3.86 volts and 70.8 milliamps. And you can just see the M and the capital A for the milliamp symbol there. The V there indicating voltage. We have actually measured the voltage in this circuit to be V equals 3.86 volts and the current I to be equal to 70.8 milliamps. The first question is, how good are these readings? Well, the manufacturer's specifications for this digital multimeter rate on a voltage measurement that the voltage reading is good to plus or minus 1.2% plus 2 digits. On a current reading, it is rated as plus or minus 1.5% plus 3 digits. Now, 1.2% of 3.86 is in fact 0.0463. However, since the digital multimeter can only read to the second decimal place in this case, it makes no sense to quote anything beyond that. So I'm going to round that to 0.05 as 0.5 there. And then 2 digits simply means a 2 in the last column, which is a 0.02. and so the total uncertainty in that reading is 0.07, and I can write V equals 3.86 plus or minus 0.07 volts. Similarly for the current, 1.5% of 70.8 is actually 1.062 milliamps, and so again I am going to round that to the last place shown on the digital meter, which in this case is the first decimal place, and round that to 1.1. 1.06 rounds up to 1.1. 3 digits simply means 3 in the last place. That added together is an uncertainty of 1.4 milliamps, and so the actual current I is 70.8 plus or minus 1.4 milliamps. Now to calculate the resistance, R is just V over I, which is 3.86 volts over 70.8 milliamps. But to convert that to amps, 70.8 milliamps is 70.8 by 10 to the minus 3 amps on the bottom line, and multiplying that out it comes to 54.519 ohms. How good is that value? Well, since I'm doing a multiplication, I can write delta R over R is equal to delta V over V plus delta I over I. Cross multiplying that up, we'll just write delta R equals R times delta V over V plus delta I over I, which is 54.519 times delta V over V is 0.07 over 3.86, and the delta I over I, as long as the top and bottom line are in the same units, that's just a pure ratio, so working in milliamps that's just 1.4 milliamps in 70.8 milliamps. And multiplying all of that out, we get a final answer of 2.068 ohms as an uncertainty. So what do? We will round the uncertainty, since the leading digits are 2, to 2 places, write it as 2.2, and then round the value to match, ultimately writing the resistance R is 54.5 plus or minus 2.2 ohms, which compares favourably to our last measurement because it is in agreement.